ladies and gentlemen. This is Ms. Skokin. We're continuing our work in inference, and this is a lesson on hypothesis testing for difference in proportions. So let's get started. Mythbusters investigated this question. Here's a brief recap. Each subject was placed in a booth for an extended period of time and monitored by a hidden camera. 34 subjects were given a yawn seed by one of the experimenters. That is, the experimenter yawned in the subject's presence before leaving the room. The remaining 16 subjects were given no yawn seed. So the first thing that we're going to do is we're going to start out with an outline of the Mythbusters experiment. We start out with 50 subjects and we randomly assign them to the two treatment groups. We're told in the verbiage of the question that 34 subjects were given a yawn seed and 16 were given no yawn seed. At the end of the experiment, they compared the proportion of yawns from the two different groups. Let's take a look at what the results were when they tabulated the data. Out of the 34 people who got a yawn seed, 10 of them yawned. Out of the 16 people who didn't, 4 of them yawned. Those are the numbers that we're going to use to come up with our sample proportions. So if P1 is the true proportion of people who yawned out of the ones who got the yawn seed, then our sample proportion is 10 out of the 34, which gives us 0.294. The other sample proportion, P2, or P2 hat, is the proportion from our sample of 16 who yawned, and that was 4 yawned, and that, of course, is 0.25. All right, so what we're interested in is the difference between the proportions, and we're going to use, we want the true difference, but we're going to use our sample as evidence. We always do that for significance testing. We think that the people who had the yawn seed have a tendency to yawn more, so we're going to put those first. That means we'll be able to get a positive result if we are in fact correct. So it's going to be 0.294 minus 0.25, giving us a difference of 0.044. All right. Now the question number 3 says, do the data provide some evidence that yawning is contagious? At this point, we're not looking for statistically significant evidence, we're just looking for some evidence. And of course, our answer is yes, because we did end up with a positive result. So that means that out of our sample proportions, at least, we saw that the people who got the yawn seed did yawn more. And our next question asks us, Adam Savage and Jamie Heineman, the co-hosts of Mythbusters, use these data to conclude that yawning is contagious. Do you agree or not? And so at this point, we have to decide if that value, which is 4.4%, is statistically significant. And so chances are we don't think it is. It is relatively small difference. So we're going to say no, it could have happened by chance alone. Okay, we've got some additional questions on the next page, so let's move on. In this activity, our class will investigate whether the results of the experiment are statistically significant or if they could have occurred purely by chance due to random assignment. All right, so we're going to start out by writing our null hypothesis. And the null hypothesis for us is going to be that we think there's no difference. So we write that symbolically, starting out with our H naught, and then remember the null hypothesis is always about the population parameter. So P1, the proportion of people who yawned from treatment group 1, minus P2, the proportion of people who yawned from treatment group 2, equals 0. This is our null hypothesis. And in plain language, we can say that this means the yawn seed doesn't affect whether or not the person yawns. If we were sitting in class together right now, we would have split off into groups, and each of the groups would have a deck of cards so that we could run our simulation. So we're going to use a deck of cards for simulation. If you have one handy, I wouldn't mind you pausing the video after we read the instructions and then trying it out yourself so that you can see how the simulation would work. We're going to start by taking the jokers out of our deck of cards, and then we're going to take out 2 red aces. That's going to leave exactly 50 cards in the deck, and it's going to give us an ability to, if we use aces, kings, queens, and jacks to represent no yawn, that gives us 14 out of the 50, which you may remember was the number out of the 50 that ended up yawning between both the yawn seed and no yawn seed groups. Next, we're going to shuffle the cards well, and then we're going to divide them into 2 piles. We're going to deal them out into a pile of 34, representing the student or the people who got the yawn seed, and another pile of 16 representing the people, the test subjects who did not get the yawn seed. And then we're going to figure out what the proportion is of each of those different stacks, the proportion of yawns that are represented, using, once again, all other cards besides the 4 kings, 4 queens, 4 jacks, and 2 aces. Okay, so if you are following along with the simulation with your own deck of cards, you can pause the video now, and we're going to do 3 trials. So I'm going to do 3 trials and put my data on the chart that you have here. You do your 3 trials, and then we'll get back together in a minute so that we can plot our data. See you back in a minute. Here are the results from my 3 trials, and what we're going to do now is create a class dot plot. And again, this is a simulated class dot plot because you realize you're not sharing your data with me, but that's okay. I'm going to provide all the data, and then we'll take some notes on it. So here's our class simulation dot plot, and the next question says, in what % of the class trials did the difference in proportions equal or exceed 29% minus 25%, which is 4%? And we find that out of 22 dots, we have 1, 2, 3, 4, 5, 6. 6 of them, 6 out of the 22, are at 4% or above. And that proportion is 27,273, let's say, rounded to 3 decimal places like we're supposed to do in AP statistics. And what we have just found is our p-value. So our p-value from the simulation gives us about 27%. And our last question, but definitely the most important one, is what conclusion can you make about whether yawning is contagious? And as always, we're going to use that 5% rule of thumb. We're going to compare our simulated p-value to our alpha of 0.05 or 5%, and that's going to lead us to fail to reject the null hypothesis and say we do not have convincing evidence that yawning is contagious. And this means we were able to prove that the Mythbusters conclusion was incorrect. Okay, let's take a look at our box of important information on the next page. Let's start by looking at the different types of hypotheses we can have in our significance test about a difference in proportions. The null hypothesis, remember, is always going to have an equal sign on it. So we're going to say our null hypothesis is consistently going to be P1 minus P2 is equal to 0. Now this is another way of saying P1 equals P2. We know algebraically that makes sense. We just move the P2 over. But philosophically, we look at one as if there's no difference. We look at the other one as the 2 things are equal. So again, mathematically those are exactly the same thing, but I just want you to think about how the question might present the information to you so that you can kind of gauge exactly how you're going to think of it. And again, either way that you write it up is fine, but typically we write it like the way that we see it on the left-hand side. So now let's talk about alternative hypotheses. The alternatives are still going to be about P1 and P2 and 0, but we're going to have different types of inequalities. So we could start off with P1 minus P2 is less than 0. And this is another way of saying that P1 is less than P2. Another possible alternative hypothesis is that we have a greater than 0. And this would represent when P1 is greater than P2. Now remember that when we do our sketch and shade, the direction of the inequality is where we show our shading. So last of all, of course, we have the possibility that we've got is that we just have a not equal to. And this is where we would see the bidirectional, the shading on both sides. And let's see. P1 is not equal to P2 would be the last one. That one, I guess, is the most straightforward. But we definitely define with the alternative hypothesis with direction. Let's take a look now at the conditions that we're going to be checking. So these are going to be the same whether we're doing a confidence interval or we're doing a significance test. And the first one is random. There are different ways that randomness can be introduced. And if we have a random sample, then that's typically when we have some type of observational study. We have a survey, for example. And the reason that we want randomness in this kind of a case is because we want to be able to generalize to the population. Whatever our conclusion is, we want to be able to generalize it or make that conclusion about the whole population. The other way that we can have randomness is we could have a randomized experiment, which means that we've got random assignment. And the reason that we want that kind of randomness is because we want to be able to establish causation. Remember, we can have correlation, but correlation does not mean causation. And the only way that we can establish causation is to have a randomized controlled experiment. And that means we have to have random assignment to the treatments. Okay, the next condition is going to be our 10% rule. And just as a reminder, we only check this when we're sampling without replacement. And remember, this is all about independence. So if we are not sampling without replacement, we don't need to check the 10% rule, but we can still make a statement about the outcomes being independent of one another, if that's appropriate, or if it applies in that situation, I should say. The third condition, of course, is going to be our large counts condition. And this is the way that we can earn the right to use normal procedures like Table A and normal CDF and z-scores. So what we're going to do is for both groups, we are going to make sure that our NP, or the count of number of successes and the count of number of failures, are both greater than or equal to 10. So when it comes to our significance test for the difference in proportions, we've got our hypotheses, our different possibilities down, and we've got our conditions down. And just as a reminder, when we graph these, we're going to have directional shading. And remember to make that part of your work. Okay, now you've got that check for understanding. So I'm going to have you turn the video off, work on the check for understanding, and then turn it back on when you're ready to check your work. See you back in a few minutes. Pay close attention to the format of the way that we write things and the way that we phrase things. And check your work. Make sure to fill in anything that you need to. If you didn't have everything filled in, or if there were some items that you need to correct. Now down at the bottom where we are supposed to list out the conditions, under large counts, you know, when we were doing the confidence interval, we did N1, P1 hat, and N11 minus P1 hat, etc. But this time, we're going to look at things slightly differently, because remember, every time we're running a significance test, we're always assuming that the null hypothesis is true. And if the null hypothesis is true, then we might look at things slightly differently. In our next lesson, we're going to look back at the prom question, but we're going to run a hypothesis test for it. So that's it for now. I will see you soon. Take care.